Hey everybody, Mr. Bennett. I've got another section of notes for you. We're looking at sound today, and we need to remind ourselves that sound waves are mechanical waves. Mechanical waves. And what that means is that they have to be carried by matter. I cannot have sound if there's nothing to carry that sound. So things like the air or solids or liquids, and that's what we're going to talk about right now. Solids, this all has to do with how the atoms are packed. So I'd like you to draw a line and then just kind of shade this area in. These atoms are packed very, very tightly. So if I were to hit one of them with a wave, a sound wave in particular, that atom jostles its neighbor, who jostles its neighbor, and that sound propagates, or it travels very, very quickly. This is very similar to taking an entire class full of people and jumping into a supply closet somewhere. If one of you gets bumped, the rest of you are going to feel that energy very quickly. Same thing could be said at a concert, somewhere where there's a lot of people put together. So solids, this is the fastest medium or fastest material sound travels through. Liquids, on the other hand, liquids still have particles or molecules, these are water molecules, that are close together, but they're not as close as solids. So they're a little bit more fluid. They move around, they jostle one another. Energy is still passed very easily from one another because they're close, but it's not quite as fast as a solid. And then finally, the gases. These particles are very, very spread out. In fact, we assume that they don't interact with each other at all when we're doing calculations. We're going to see those in another chapter when we get into the chemistry side of things. So sound travels very, very slowly relative to solids in gases. So this is the slowest. Now, we experience sound in gases most often, but we're going to be playing around with sending sound through solids and see what the difference is. And this is also a good reminder that a sound wave itself is a longitudinal wave. So it is caused by compression of some kind. So in this box here in the middle, we're going to draw a longitudinal wave. And we've done this with the spring, but now we're going to be looking at particles. So we're going to start with a compression, and this is just kind of a dark area. Okay, so this would be an area where particles are compressed together because of a sound wave or vibration of some kind. And then in between that, remember, we have this thing called a rarefaction, which is where the particles are kind of spread out. And then we've got another dark section here, and then another rarefaction where particles are kind of spread out, and then another compression. And this goes on and on and on. And there's two things we can measure with this. So while I finish drawing this, the width of the compression, the actual thickness of it, is a measure of the amplitude. So if we were looking at this guy, just that distance is the amplitude. And we can also measure wavelength, and that's done the same way. So we look at the distance from one wave to the next. So we can still measure frequency, we can still measure amplitude. And this brings us to another kind of, let's make the connection. Loud sounds have a high amplitude. There are strong compressions, and quiet sounds have a low amplitude. And conversely, high-pitched sounds have a high frequency. We hear more waves going by than low-pitched sounds, which have a low frequency. So this is the experience of sound. And then also we need to pay attention to the medium. Now, really quickly before we finish, I've got a little picture here. This is called an oscilloscope, and this will take a sound wave and translate it into it'll look like a transverse wave. So what it lets us do, we can see this is what a note sounds like. Its frequency is 261 hertz, so 261 waves per second. If I were to increase or jump to a higher note, the frequency has increased. It's doubled up to 523. Same thing if I go backwards, my frequency is half of what my original note was because I've gone a full octave below. So our sounds, the ones we hear, the pitches, are due to the frequency. Volume is the amplitude. So again, here's my note. My volume is kind of towards the middle. If I were to decrease the volume significantly, those waves get much shorter. And if I were to increase them, they get a lot taller. So that's sound in a nutshell. What we need to do now is I would like you to take a look at these two things. I've called these critical thinking questions. They're just ways for you to kind of take this and package it up in a question format. And then we've got a writing prompt. I would like you to do these right here on the bottom of the page. There's about a half sheet below this. You can flow onto the back if you need to. But take a look at these questions, do the writing prompt, and I will see you in class.